Thanks for the introduction. So I will be talking about HiPy, which is a framework, a novel framework for extracting the high-level semantics from Python code for data processing. And the motivation is really coming from practice, from data processing systems, database systems, and how do they work? Maybe a quick reminder. You usually start with something like a SQL query, and then the systems pass this query into, for example, a logical plan with different operators. And then what's really crucial, they usually optimize this declarative query, for example, by reordering operators and other kinds of optimizations. And that's where you get asymptotic speed up compared to a naive implementation. And then what a lot of modern high-performance systems do is they then generate a nice code just in time to get really a high-performance execution. And that's great, that's state-of-the-art, but unfortunately a lot of users don't like SQL, so they kind of write then their complex business logic in Python. And the bad thing is that if we just use what the user gives us, we end up with basically black box operators for which we don't know anything. And this means we cannot do query optimization, we don't get our big speedups, and we also can only kind of generate really degenerated code. This is where a lot of performance goes down. What we would kind of want is some kind of method to understand what the user is writing, to extract really high-level operators, for example, out, but also understand, for example, scalar functions and so on, so that we can then, in the second step, use this to inline basically what the user wants into the logical plan. Then we can do query optimization again, and we generate a much more optimal code. And it's still okay if maybe a bit of Python remains, but most of it is now really optimized. And in this talk, in this paper, we are really covering the first part because that's not an easy problem, because Python is Python. And there are basically three things that we want. The first one is we really want to extract the high-level semantic. So I mean, it's already some of a benefit if we would get like statically typed IR like LVM or whatever out of Python, but we cannot do high-level optimizations. So we really need the high-level semantic. What's going on the high level? What did the users want to compute? The second thing is that Python is really complex, and also users often don't restrict themselves to simple Python code, but they will use complex features and so on. So we really want to handle real-world general Python code. And then also Python has become that much used because they have this rich ecosystem of a lot of high-level frameworks, libraries like Pandas, NumPy, scikit-learn, whatsoever. And users will, in most cases, use these libraries and not write like 3 levels of nested Python for loops. So we also need to kind of capture those libraries. And there is a lot of prior work around Python. So there is a whole class of compilers and similar systems that try to make Python faster, either ahead of time or just in time. And yeah, depending on the exact workload and so on, it usually works quite well, but you cannot really do high-level optimizations on it. That's not what they are aimed for. Then there are more specialized compilers. Probably the most well-known one is Number for optimizing kind of NumPy-centric Python programs. And in their respective domain, they also target high-level optimizations, but they usually only support a quite narrow subset. And then there's a lot of work around supporting embedded DSLs in Python. A lot of work also in the direction of machine learning frameworks, where the goal is to extract high-level semantics, so basically extract graphs of operators that are formulated as embedded DSLs and so on, but they're usually geared towards capturing everything that basically interacts with their DSL framework, and everything else is just eagerly executed in Python. So in contrast with HiPy, we really want to extract the high-level semantics, but for general Python code, and also with heavily used libraries and frameworks. So how does it work? So users basically write their Python functions and then annotate them, and actually this annotation will then transform the Python function into a new Python function that serves as program generator. So it basically rewrites the function, adds another argument, and then reroutes every statement, every expression to basically through this object. And when we run this function in using Python, we then get a nice statically typed intermediate representation that is basically the goal is that it's on the same conceptual level as the Python function. And then on this IR, we can then run high-level optimization and also generate code. And for this paper, we then generated C++ code. The IR is SSA-based, also covers like high-level types like n-dimensional arrays and tables. And it does not contain basic blocks, but models control flow by basically supplying callback functions to high-level operations. To give a bit more detail of how this first transformation looks like, for a bit of a more complex case, the function itself basically just received this additional parameter. The variable initializations get rerouted through this context object, and also the loop body gets just rewritten so that the binary operations get rerouted. For the loop, we rewrite it to be basically a nested function that gets the current element as well as the values that are written to read and written to in the loop, and it then returns the updated values. And then in the end, we kind of pass the responsibility towards this generator object. And then if we run this function, it will produce this IR. So one of the big challenge is that handling general Python code is not simple, because Python is really complex and it's not been made to be analyzed and so on. And the main idea is that in the worst case, we fall back to Python. So if the user writes crazy Python, he will get Python. But he will not notice it, so it will be transparently. So everything that's kind of undetected or we don't know something about will automatically then use Python in the background, and it's also fine-grained. So if you basically have 90% of a function that's, let's say, reasonable, we know the semantics about, we know what it's doing, and then at the end there's like 10% that we don't know something about, then for this part the idea is that Python will be used as a fallback, but users will still benefit from the other 90 parts being understood. The benefits of this is that you can basically support any Python function, because in the worst case you will just run Python, but you get this nice gradual performance regression. The more tame your Python function is, the better it works. The more unsupported features or unknown libraries are used, the less you can do. The one downside of this approach is that it comes with a bit of complexity to get it really right, especially if you use this fallback mechanism, basically end up with two runtimes, your kind of native runtime and your Python interpreter, and especially with mutable objects, you really need to make sure that this original semantics is preserved and there won't be any inconsistencies. And we deal with this a lot in the paper, but for time reasons, I won't go into more details. So on the practical side, how can you imagine that this is working? So the generated intermediate representation contains also a Py object type that basically corresponds to a Py object pointer when you use basically embed Python into your process using, for example, C. And then it also contains some operations like accessing attributes or calling Python objects. for a small example where it's really a lot of tools in this domain will just break down is if basically the type of X depends on some value. What we will basically end up in the IR is we generate an if expression, if statement, where in each block you just do what you want to compute. In the first case, we have an integer constant, in the second one, a float constant, and then because you have kind of different types, you need to bring them to a shared type, which means we will go to Python. Convert both values to Python objects, and then we have one shared type. So the last thing is supporting the ecosystem. So as I said before, Python users will use this ecosystem of optimized libraries like pandas, NumPy, and so on, which already is like a local minimum. It's good, much better than writing Python code itself. But if you really want to bring it into, for example, database systems, you also want to understand what's going on. So with HiPy, we have a modular approach where you kind of implement or define the semantics for arbitrary Python libraries. So you can basically say, oh, I know that this pandas function does that and that, and then HiPy will generate the IR for that. And the nice thing is with the fallback mechanism I just talked about, we only need to implement what's really crucial. So we may want to implement the topmost 30 pandas functions, and that's what most users will maybe use. But we don't need to implement the semantics for every single pandas function, because for this we can just fall back to Python. So for the prototype system, we presented with the paper, we implemented irrelevant parts of the built-in module, NumPy, pandas, scikit-learn, and so on, and everything else is then going through the fallback mechanism. So like a small peek of how this looks like. For the list sort method, you basically then define a list class with a few annotations, and then you, in the sort method, you first generate a compare function that basically can compare two list elements, and then through this intrinsics module, you then generate a high-level sort operation that will then be emitted in the IR. So we integrated everything into an end-to-end prototype that then also runs some optimizations on this high-level IR, like that code elimination, function inlining, a few forms of canonicalization. For more numerical workloads, we can use array operations, so you basically only run once over the array, not multiple times. And for tabular data processing, we turn column-centric operations that are very frequently used, for example, with pandas. You first get a column of your data frame, then do something on it, and then set it back into really table-centric operations. You say, oh, I'm basically doing apply or filter or so directly on the table. We also can then push down operators if you know that has the same semantics, and you can also fuse table-centric operators. For the C++ code generation, for this prototype, it's really simple. We just put together string patterns in Python, and in the runtime library, we use bind11 for embedding the Python interpreter. We have a basically n-dimensional array component that implements a subset of what NumPy does, and also Apache Arrow for representing tables in memory. And for the future, you want to really do this in a proper way, not in a standalone research prototype. So the idea would be to use MLIR for the IR that is generated, and then integrate this into our existing MLIR-based query engine. For the evaluation, we looked at a few different workloads. So the first one is data science and engineering, where you have a lot of pandas with a lot of custom Python code and so on. And we see that our approach is the rightmost blue one is quite good. Depending on which optimizations are possible, you get really huge speedups, even if you need to use the fallback mechanism, which is indicated by the small warning sign on the top. For numerical computations, so basically NumPy, it really depends on which scenario you have. So these are all benchmarks that are already there. And for the first two, it's basically just chaining vectorized NumPy functions. So there's already a lot optimized. There's not so much to gain. We gain a little bit, but okay. The other two, so Laplace is basically getting in the loop submatrices of your matrix and then doing vectorized operations. And then the last one is basically you really just use NumPy as storage container and implement your custom algorithm in Python. And this is where Number shines most, but we are also getting like 150x speed up. And in between Laplace, it's where we even beat Number because apparently it really cannot do much about that. But again, this was not the primary focus. It was more about for database systems and user-defined functions, where one could, for example, also use NumPy, but it apparently also works for this. We also looked at general Python performance with existing benchmarks. And for the first three ones, we can see we can handle also complex functions and achieve quite nice speedups also compared to existing and established systems. For the latter two, they basically serve as evaluation for this fallback mechanism. So as you probably know, a Mandelbrot algorithm heavily relies on complex numbers for everything, and HiPy doesn't know about complex numbers. So for every computation, we use Python, which comes with slight overheads, but we're still more or less at the same performance. So if users really write functions that we don't know anything about and fall back a lot, then we still get kind of Python performance. The same with the other benchmark with telco that relies on decimal computations, which we don't support yet. So conclusion, with HiPy, we present a novel approach for extracting high-level semantics from Python code by first generating program generators in Python, and then we run them in Python to generate a statically typed IR. Then with this fallback mechanism, we can gracefully fall back to the Python interpreter instead of just waving with the hands and telling the user that you're doing something wrong. It's also modular, so you can define high-level semantics for any Python library, even if it may be implemented in C++, assembler, Fortran, or whatever under the hoods. And with the end-to-end prototype, we showed the potential of high-level optimizations and generate efficient C++ code from there. Yeah, got a lot of speed-ups for data science workloads, but also for other domains and general Python. Thank you.
All right, we have time for some quick questions. Let me start us off. Python has been famously resistant to optimizations in the implementation for a long time, but that's starting to change. So I think a week or two ago, they shipped their first copy batch compiler based JIT, for instance, and there's real concurrency in there right now. So I mean, how do you think the sort of cost benefit sort of analysis of these kinds of methods might change going forward?
So your question is how these improvements might also improve the analysis capabilities, or?
I mean, so it seems to be that Python is also going to is also getting faster for the first time. So how much more will we have to do this kind of stuff?
I think it depends a bit on what your scenario is. So if you just want to run, basically make Python programs in general faster, like your Django web server or whatever, then I mean this helps a lot. Our motivation is really we have our established system there, and we want to conceptually inline Python code because there's a lot to gain, especially in the context switches and so on. So in this deep integration, and I think that's something that won't go magically away if you have a JIT compiler inside Python.
So we'll take one question, and with the next speaker, please set up.
Cool. This is really cool. I just had two quick questions. The first one is, have you identified many opportunities where you can release the global interpreter lock in the C++ code?
So I mean, we haven't looked that much into the interpreter lock because I think that's more into the low-level technical details, which of course are becoming more relevant if you then use our approach to really integrate it into systems. But yeah,
And then the other one was, I imagine there are many cases where you kind of are hopping between language boundaries, where you need to go back into Python to make some method call that goes back into C code, like in a library like NumPy or something. Like, do you see like an opportunity there to make the call directly from native code to native code and remove kind of hopping through the Python interpreter to get there?
I mean, we haven't investigated that, but I mean, that would be a nice idea to, if you understand enough that you know that it will, for example, end up in this part of the NumPy code, but you don't want to re-implement it or handle it yourself, you could kind of skip Python in between. Yeah.
Okay. Cool.
Right. Thank you.